Okay. Okay, so thank you very much, Joachim, for the introduction and also for asking me to give a presentation here. So indeed, I will give a presentation on the recent work that we did on applying the phase field models to what I would say truly multi-component alloys. So alloys with at least 4 elements. And I think this will be a very powerful tool in computer-aided design of these alloys. The work that I present was mostly performed within a number of PhDs, namely the PhD of Xiaojing Zhuo, Yuri Coutinho, and Saurabh Chatterjee. So I think today there are many opportunities to apply the phase field model towards multi-component systems, because there are, for example, the new high entropy alloys, where it's very important to understand how we can modify the microstructure by changing composition, by heat treatments, and so on. And there are also new processing techniques like 3D printing that give us completely new microstructures. And actually, for many of them, we still don't understand how they will behave and how we can manipulate the way that they will behave. And they become more and more complex, and then of course simulations become very important, and you need simulations that can take into account many effects, the effects of many components, and also some effects of stress and interfacial energy. So I think that's actually where phase field modeling comes in. So it can give us more insight in the process structure relations, and also gives us a way to study this relation before you do experiments. And I also think that if you would combine phase field simulations within a multi-physics framework, so combine it with mechanical models, combine it with magnetic models, and so on, then you can also use these simulations somehow to study also the relation between structure and property, and even make the full triangle then. But of course, there are also still some challenges, and that's also why you don't find so many papers where the phase field method is applied, for example, to high entropy alloys and considering all the components. And I think one main challenge is that, yeah, if we want to study microstructure evolution, we have to spend various length scales and various time scales. And today that still requires a long computation time. Sometimes within scientific settings, this is possible, but for example, in an industrial setting where you want to have an answer in 1 or 2 hours, this is not yet possible. And another large challenge is that the more components you take into account, the more input data you will need. So the phase field method is a phenomenological approach. And we know that many of the phase properties and interface properties, they all depend on the composition. So the more composition variables you have, the more complex the dependence is. And the problem is not only that you do not have the data, like it is, for example, for interfacial energy or for elastic properties, but even if you have the data, as for example, bulk energies and diffusion mobilities, which are today often available in thermodynamic databases, even then it's difficult to couple it with the full complexity and run your phase field simulations. And it's about this second point that my presentation will be today. So first, I will give a short introduction on the phase field model, just the basics, then a short introduction on the Calphad models. And of course, I will put the focus on these things that are important when you want to couple both of them. And then I will also illustrate what is now the problem if you want to go to, for example, a quaternary alloy. And after that, I will then discuss a number of techniques that we have developed within these PhDs to somehow circumvent these challenges and make quaternary simulations possible. And I will also show some applications. So as many probably know, but maybe not everybody, in a phase field model, we will use phase field variables to represent a microstructure, and we typically take as one phase field variable per phase, or if you have several grains, then you will use phase field variable for each grain. And these phase field variables, they are defined in such a way that the phase field variable that, for example, represents here the BCC phase will equal 1 within the BCC phase, and it will equal 0 in the other phases. While the phase field variable here, that is, for example, representing a sigma phase, it will be 1 within the sigma precipitate and then 0 within the other phase. And of course, at the interface, we will have a kind of smooth transition in the values of these phase field variables, and that's the way that we can follow the interface. Besides phase field variables, we will also use molar fraction fields. So we will give the composition as a function of position using molar fractions. For example, for this alloy, it's a quaternary alloy, and then we will use the molar fraction of aluminium, chromium, and iron to describe the local composition at every point. So also these molar fractions, they are a function of space and time. And if your microstructure is equilibrated, for example, then again, in the precipitate, you will get the equilibrium compositions of the precipitate outside those of the matrix. And at the interface, you have then a smooth transition between these two values. If you are not in equilibrium, then of course you can have gradients in composition within the phases, and the composition will deviate from the equilibrium composition. Then we formulate a free energy functional, which typically contains what we call a homogeneous part, so a part that only depends on the local values of the phase fields and the composition, and which has also gradient contributions. These gradient contributions are important to obtain this diffuse interface and will also contribute to interfacial energy. This free energy functional is the basics of the model. And so, for example, this homogeneous part will, for example, contain the bulk chemical energies of the different phases, but can also contain elastic contributions and so on. From this free energy functional, the evolution equations of the phase fields and the composition variables are derived in such a way that the free energy decreases in time, and of course that you have mass conservation. The second equation here describes how the composition varies. This is actually a generalized diffusion equation, and here you can see that we will also take into account cross effects. So the gradient in, for example, the chemical potential of aluminium can drive then the diffusion flux of chromium or something like that, because it turns out to be important in these multi-component alloys. So then when we look at the link with the Calphad Gibbs energies, then it will be in this part here. So this part, in the most basic model, it will consist of the bulk chemical energy and a multi-well that is needed for the interfacial energy. This bulk chemical energy can be formulated as an interpolation between the Gibbs energies that you can find in Calphad thermodynamic databases. So this is the molar Gibbs energy of a certain phase. We just have to divide it by a molar volume value. So here we can, for these Gibbs energies, we have in fact data available for many systems, and it's just that we have to find out how we can get them into the phase field model. And then there is also a coupling possible for the diffusion mobilities here. So this mobility here in the phase field model is in fact an interpolation of diffusion mobilities of the different phases that are present in the system. And they can also be taken from the Calphad mobility databases. So now let us look at the Calphad Gibbs energy models that are available, because we need them to formulate the bulk chemical energy in our phase field model. We know that they always consist of these three terms. So there is the reference contribution, there is a contribution from ideal mixing, and then there is a contribution from interactions between the different elements. And then, of course, you can also have physical interactions, magnetic effects, and so on. But they were not present in our system. Depending on the characteristics of the solution, we will use different types of models. And depending on the type of model, the formulation of these different terms will be different. So the simplest one is a substitutional solution model. In that case, all three terms are expressed as a function of the mole fractions of the different elements. And these are the same mole fractions as the mole fractions that we use in the phase field model. So in fact, in that case, if we have this reference energy and if we have these interaction coefficients, we could just implement all these expressions in our phase field model. We can also do that for a quaternary alloy, and that in fact it works, and it works well. Of course, if the database is encrypted and we don't have the coefficients, then we have to find another way. But there are also other more complicated models. So another one type of models are the sublattice models and the order-disorder models, which are used for mostly for the intermetallic phases and the phases with a more complex structure. In that case, it is assumed that atoms typically mix within one of the sublattices. And so we have to define what we call side fractions or sublattice fractions that give the fraction of a certain element on one of these sublattices. And the Gibbs energy parts, they are then formulated as a function of these side fractions. These side fractions, they of course relate to the mole fractions, but you cannot just compute them in an analytical way based on the mole fractions in the general case. They have to be obtained by a minimization procedure. So these side fractions will be in such a way that they minimize the Gibbs energy. A thermodynamic software like thermocalc can do that, but we cannot do that in the phase field simulations. Or if we would like to do that, that would take a lot of time because we have to compute all these expressions at every grid point in our simulation and at every time step, and that would take too much time. So a direct coupling is not possible for this type of models. And then you have also other models. Actually, you have many more models, but another one that is also used a lot is, for example, the quasi-chemical model. And also for that model, bond fractions and side fractions are used to formulate these Gibbs energy contributions. And again, they have to be obtained by a minimization procedure. So again, we cannot use these formulations in our phase field simulations. So that's already one of the problems that we encounter when we want to make general multi-component and multi-phase models. The same is there for the Calphad diffusion models. So if we look at diffusion in a number fixed frame, then we can express the diffusion mobilities, the different diffusion mobilities of a certain phase, starting from atomic mobilities of the different components. And these atomic mobilities follow an Arrhenius temperature dependence with a prefactor m here, m rho 0, and here is then the energy term Q. And it is these two terms that are modeled in the diffusion mobility databases. Again, for each of these terms, we have a reference contribution and a contribution to mixing. And it depends again on the type of material that you're looking at, what will be the format. So for a substitutional solution model, it can again be expressed as a function of the molar fractions. Here is a mistake. It should be the Q. But if you look at sublattice models, again, we will need both side fractions and mole fractions to express these atomic mobilities. So again, it will not be possible, even if you have the coefficients, to put it directly in the phase field model. So to summarize, what type of coupling methods could be used to use the Calphad data in the phase field models? So a first one is that you use the expressions, the Gibbs energy expressions, but that's only possible if you work with a substitutional solution and if you have all the coefficients of the model. So that's certainly not the most general solution that is available today. It will only work for certain types of phases. Another approach is to use a programming interface with a thermodynamic software to compute at every point the thermodynamic data that you need. But it turns out that having this interface slows down the program. So it takes time to call a certain function, and you have to do that at every grid point. If you work with dilute solutions and binary solutions and even ternary solutions, people have developed methods to minimize the number of times that you have to make a computation. But these methods are, of course, based on interpolations and extrapolations, and mostly linear interpolation. And if you want to do that for a quaternary system, actually it requires a lot of computations, and also the interactions between the different elements are stronger, and so your interpolation, a linear interpolation, is not always that accurate. So then another method is the one of the data extraction. So where you first compute all the thermodynamic data that you need, so Gibbs energies and the chemical potentials and atomic mobilities as a function of composition, and you put them in a kind of table or a list, and you know which data point is where. And then when you run the simulation, you look up and you search for the data point that you need. And so I think this is the most general approach, because it can apply to the phases that are modeled with a sublattice model. You can also apply it when the database is encrypted. So this is generally applicable, but there are some problems with it. So let's look at this method. So imagine you have a binary system, and you assume a collection step of mole fraction of 0.1. This is much too large. If you want to make an average, a very accurate phase field simulation, you need at least 0.001. But just for the illustration. So for a binary system, it means that you have to pre-compute 10 data points and you have to store 10 data points. It's not much, and it will work very smoothly and easily. Even if you have to take 0.001, it's just 1,000 data points. It's also not a problem today. If you go to ternary systems, then you have two independent composition variables. For the same collection step, you would need 100 by 100, no, 10 by 10 divided by 2, so approximately 50 data points. Still doable, even if you go to, for example, 100 data points for each variable, it would already be 5,000. And if you go to 0.001, it would even be higher, but it's still possible to do this for a ternary system.
Is die niet dan automatisch aan? Nee.
Is there a question? Okay, but so we want to do that for a quaternary system. And then you have an extra dimension, and you can already see that the number of data points that you will need, that you have to pre-compute and store, that it will blow up very quickly. This graph illustrates this. So here we have computed or estimated as a function of the number of components that you will want to consider and the step size that you need, how many data points you would need. And this here is a logarithmic scale. So you see that by decreasing the step size and by increasing the number of components, the number of data points that you need really blows up in an exponential way. And practically, this means that we can use this approach for ternary systems, but not anymore for quaternary systems. It's not just a matter of waiting longer, it's just not possible. So as soon as we want to go to quaternary systems, we have to find other approaches to minimize this number of data and to work more efficient with these data. And so for the remainder of this presentation, I will show a number of techniques that we have developed to deal with this challenge. And the first method that I will show is still a very simple one. It's not generally applicable, but it works very well and very accurately for this particular system. So that's why I like to show it. In this method, we will just use a local fitting of the Gibbs energy curves. So in this research, we wanted to study the FCC to BCC phase transformation in aluminium, chromium, iron, nickel systems. And this is interesting because it is seen that in these systems, so the amount of aluminium can be used to play with the amount of FCC and BCC phase. And the more FCC you have, the more ductile your alloy is, the more BCC phase you have, the stronger it becomes and less ductile. This is well studied for aluminium, cobalt, chromium, iron, nickel, but less for the quaternary alloy, although this alloy is believed to have similar advantages. So the idea is to simulate this phase transformation at 700 degrees Celsius. And so we first verified where we have this two-phase region in our quaternary phase diagram. So to do that, we computed sections of the quaternary phase diagram for at 700 degrees Celsius and for different amounts of aluminium. So the molar fraction of aluminium goes from 0.01 up to 0.07. And then you see that in this range of the phase diagram, you have here a two-phase region. If you have more aluminium, then it disappears and you go to a three-phase region. But the idea was to do a simulation of the transformation in this area. So the first thing that we did was determine this two-phase region. And then we extracted the Gibbs energy and the Gibbs energy over a region that is a bit larger than this two-phase region, because then in fact we have enough data to simulate this transformation. It's still a lot of data. You cannot just work with these data in the simulations, but we were also lucky in this system because both phases behave as a substitutional solution. So in fact, we know how the expression, the Gibbs energy expression, should look like. We know it has a reference contribution, ideal mixing, and excess. And for the ideal mixing contribution, we know that it looks like this. So we can, in fact, split this up and we can compute it separately. And then we found out that the remaining parts, they fit very well a polynomial function of low order. So very accurate and very easy. That's not always the case, but for this system, it worked very well. And so that's actually what we did. So we pre-compute the Gibbs energy using thermocalc. We subtract the contribution from ideal mixing, and the rest is then fitted using a polynomial function. And in our phase field model, we use this full expression. We can also use this to compute chemical potentials and diffusion potentials. For the diffusion mobilities, we were also lucky because the atomic mobilities turned out to be almost constant over this two-phase region. And so the composition dependence can be implemented in our phase field model using this expression. So in a very simple way, we had actually all the thermodynamics and all the kinetics that are available in Calphad databases. We also validated this, of course, so we compared DICTRA simulations with one-dimensional phase field simulations. And what we show here is the evolution of the mole fraction of chromium as a function of time obtained from the DICTRA simulations and from the phase field simulations. And you see that the behavior is very similar. And also when we look really point by point and compute the difference in composition, we found that there is almost no difference. Only at the interface, of course, there is a huge difference between the phase field model and the DICTRA model, but that's because phase field assumes a diffuse interface and DICTRA, a sharp interface. But if you look, for example, at the position of the interface and compare it for both, then you see that it's almost the same. So here we see a deviation, but this is a deviation of less than a grid point in our simulations. So it's almost exactly the same, meaning that we have taken into account all the Calphad information in a very accurate way. Then, of course, we used this model to study something, and we wanted to study the effect of aluminium on the growth of the BCC phase. So we did the same for the ternary system. And then we have also our quaternary system. For the ternary system, we simulate the phase transformation for an equimolar ternary system. And for the quaternary system, we take a system with a mole fraction of aluminium of 0.05. And the remainder is then distributed equally over the three other elements. And then we initiate the system with two nuclei, two small precipitates on an FCC grain boundary, because that's also what we see in the experiments, that the BCC phase grows on FCC grain boundaries. and then we let these precipitates grow. And we do that for both systems, and we compare then the volume fraction of the BCC phase in both cases. And what we clearly see is that in the system with aluminium, the BCC phase is promoted. So finally, we have more BCC, and the growth is also going faster. We have also compared this with experiments. So in the group of Pascal Jacques at the university at UCL, they have done experiments. So they also did annealing experiments at 700 degrees Celsius for the alloys with the same composition, and they measured the BCC volume fraction. Also, they find that if you have more aluminium, the growth of the BCC phase goes better. You obtain more, and it also goes faster. The time is very different, but I think that is because in the experiments you need nucleation, while in the simulations we already started from a precipitate. But what is important to see here is that, in fact, all this information that we have from the Calphad databases predicts that aluminium promotes the growth of the BCC phase. And that's also what we see in the experiments. So qualitatively, the predictions of the database are certainly in agreement with the experiments. But here we have also the simulations. So we can also try to understand why this is. And of course, there is the thermodynamic driving force. So if you do a calculation, you will find that the final volume fraction of the BCC phase is higher in the alloy containing aluminium than in the other one. But what we saw in our simulations is that not only the thermodynamic driving force is higher, but also the diffusion mobilities are higher in the alloy containing aluminium, although it's just a small amount of aluminium. So what we did was we extracted the diffusion mobility values for the different components at every point in our system, and we took the average because it varies, of course, as a function of position. And we found actually that for each of the components in the tensor, it was always higher in the aluminium containing alloy than in the ternary one. So if we look for the BCC phase, for example, the red bar is the one for the aluminium containing alloy, and the magenta one is then the one for the ternary alloy, and it's always lower. And this is a bit surprising because people always talk about the sluggish effect of high entropy alloys. So the more elements you add, the slower the diffusion would go. But so for this alloy, it turns out that aluminium actually increases the diffusion mobility in the FCC phase, meaning that the growth of the BCC phase goes faster, but probably also the porosity. So that was one technique that we applied to this particular system, but that certainly doesn't always work. Then we also have more complex techniques. And one of them is the tensor completion technique. So here we actually exploit the fact that we can interpret this Gibbs energy data as a function of composition, that we can interpret it as a high dimensional tensor. So in this case, it's not a stress tensor or a strain tensor, but it's a high dimensional data set. That is what we mean with the word tensor. And in algebra, it is known that you can decompose every tensor in a summation of outer products of vectors. So if you don't know anymore how you do an outer product, if you have just a two-dimensional tensor, so a matrix, then you could compute outer products as the vector u1, u2, u3 multiplied with v1, v2, v3. Then at the first position, you get first element of the first vector multiplied with the first element of the second vector. This element is first element of the first with second element with first element of the second, and so on. So this is the outer product. So this means that we can in fact represent this huge amount of data with less data, depending of course on how many terms you need in this expression. The number of vectors in each term depends on the dimensions of your tensor. So this is a 3-dimensional tensor, then you have 3 vectors. If it becomes a 4-dimensional, you get 4 vectors. The number of terms, we call it the rank of the tensor. There is always an exact relation possible. It's difficult to obtain this exact relation. It's also difficult to obtain what should be the rank for the exact description. But we know from many previous applications that if this data tensor represents physical data, meaningful data, then usually you can approximate very well this tensor using a limited number of terms here. And with limited, I mean something like 10 or a bit more or less. And so the idea here is to apply this method then to the chip's energy data and atomic mobility data. So finally, then, if we put all these vectors into matrices, we can collect them. Then you could use this as an input of your phase field simulations and use these vectors to extract chip's energy data for certain compositions. And there exists also software to compute all the elements in these factor vectors. They can be obtained using a minimization procedure. So typically you compute a lot of chip's energy data, you call it the training data, and then all these elements in these factor vectors, they will be determined in such a way that the difference between the computed chip's energies and the approximated is as small as possible. And the advantage is then that if we go to a higher order system, now the number of data that we need will not grow exponentially, but will just grow linearly. It will just be one extra factor matrix in our description. And the effect of it is also shown here. So imagine you would represent the whole tensor. The number of data depends exponentially on the number of components. But if you use this tensor decomposition, it will only grow linearly with the number of components. The exact number of data points that you need will, of course, depend on the rank that you will need for an accurate description. And this is something that we still have to try out for the chip's energies. Okay, so first we tried this out for a substitutional solution. It's silver, copper, nickel, tin, because we had the database for that system. So we computed some training data, validation data also. And the idea is to use this to fit a tensor description for a tensor with a step size for the composition of 0.0001. So a very accurate description of the composition dependence in hopefully less data points than you would need if you computed the full tensor. And then we evaluated what would be the best rank to do that. So we optimized models assuming different ranks going from 3 up to 10. And so you can see that if you increase the rank, of course, the relative error becomes smaller and smaller. But you can also see that if you go to 7, 8, 9, 10, you don't gain that much. And actually, we are here already at a relative error of 10 minus 6. So really a very low relative error. So we decided to continue with a rank 6, and we decided that that gives a sufficiently good approximation of the chip's energies. And then we use them in phase field simulations of spinodal decompositions. So we also used tensor models of different ranks. So we used rank 4, a less accurate one, and rank 6, which we consider as the best one. And then we also performed simulations using the full chip's energy expressions. And you can see that if you use rank 4, there are still some differences. So it matters actually, these small deviations between the chip's energy and the approximations. If we go to rank 6, you have already a quite good resemblance with the one that you would get with the full expressions. Certainly, if you look at the microstructure in a statistical way, so if you look at how many points have which composition, then you see that rank 6 gives an almost exact match with the full expressions. So we thought this is a very successful method. And then we also tried to extend it to more complex Calphad models. And it was also by Inge Bellemat from UGent. It was extended towards the simulation of iron 304 crystals in a quaternary slag. For this slag system, a modified quasi-chemical model is used. So no longer a substitutional solution model, so we cannot compare with the full expression. It also behaves in a more complex way as a function of composition, but still we found that very good accuracy for a rank 10. And more important to consider here is that actually before she was not able to do these simulations for this quaternary system, while with this tensor decomposition, she could do the simulations with very good accuracy. And one last slide about this method to explain you why I like it. I know it's a quite complex method. You have to know something about algebra and about tensors, but it's also a nice method because it's both data-driven. It has the advantages of a data-driven method, but on the other hand, you can also include knowledge that you have. You can include knowledge on the system, and I think that is really an advantage compared to standard neural networks and machine learning techniques. And that's also what we did. So I didn't want to go into detail, but actually in all these factor vectors, we did not assume that these were just numbers, but we assumed that all these numbers here were actually the evaluation of a certain function. So actually we did not have points here, we had functions. And because we have functions, we can take a derivative of this function. And that made that actually we could combine Gibbs energies and the chemical potentials all within one tensor model. So we developed one tensor model and with this function. And if we just evaluate the function, we have Gibbs energies. But if we first take the derivative of that function and then evaluate it, we have the chemical potentials, and they are fully consistent with the Gibbs energies that we are using. And we also optimized all these data points using computed Gibbs energies and computed chemical potentials. And so I think if you exploit this further, it will give you a very nice and very consistent description of physical data. So that's also why we want to continue with this method and also, for example, develop it for sublattice models and so on. But nevertheless, we also wanted to compare this method with what you can do with neural networks. So this was done within the PhD of Yuri Coutinho, actually the previous one also. And he developed two types of neural networks that can also implement a coupling between phase field and Calphad. The first one is a very nice one, at least if you have the database available. In that case, he develops a neural network that converts mole fractions into sublattice fractions. So it actually tackles this, well, this problem that we use a different way of expressing composition in the phase field models and in the sublattice models. But besides that, it doesn't do more. So in your phase field simulation, you still use the full Calphad expression and you have still all the physics that we have in this expression. But of course, you need all the data points here. He applied it again to the aluminium, chromium, iron, nickel system, but now a different phase transformation, one that was inspired by some experiments that Ulrike from Access showed to us. So actually, she showed us this phase diagram and also this nice microstructure. So it turns out that in this system, if you are in the section iron 2, nickel 2, that's this section, and you start in the B2 phase, then you could, for example, either go to the A2 plus B2. So these are two BCC phases, one disordered, one ordered, and then you get a spinodal decomposition. But you can also go straight away, and then you could, for example, immediately form FCC phase plus the spinodal decomposition, and that gives a very interesting microstructure. And so at Access, they were studying this microstructure. And Yuri tried to first simulate the spinodal decomposition, and later on, he also simulated actually this concurrent phase transformation and spinodal decomposition. So in this case, the Calphad models of the A2 phase, so that's the disordered BCC phase, is actually a substitutional solution model. And the B2 phase is modeled with 2 sublattices. But actually, they are both modeled with one Gibbs energy expression that is the one for an order-disorder model that consists of one term for the disordered phase, which is expressed as a function of molar fractions, and then a part due to ordering, which is expressed of sublattice fractions. And so here we have this problem because we don't know them based on the information that we get from the phase field simulations. Also for the atomic mobilities here, an order-disorder model was used. So again, we need sublattice fractions to evaluate the atomic mobilities in our phase field model. And the idea of Yuri was just to develop a neural network converting mole fractions as the input layer to sublattice fractions as the output layer. And then he uses the Calphad expressions, which are a function of these side fractions, to evaluate Gibbs energies and chemical potentials. He pre-calculated approximately 10 to the power 4 data points. So that's 10 to the power 4 compositions. And for each composition, he computed what are the side fractions. Then he was also a bit lucky to see that actually the side fraction of the vacancies on the second sublattice is almost 0. So this, if you know that, then there are a number of side fractions that depend on each other. So we could minimize the number of side fractions for which he had to optimize this model. And then he optimized several models, neural network models. So he modified the number of hidden layers, and he also modified the number of nodes per hidden layer. Besides that, he used all very standard conditions of this network. And he found out that the best accuracy was obtained using only 3 layers and 32 nodes, which is actually a very small and very simple model. It also you can evaluate it very fast in the phase field simulations. The error is then on the sublattice fractions is then something between 10⁻⁴ and 10⁻�3, so quite accurate. And if you use these side fractions to compute Gibbs energies and diffusion potentials, yeah, the error increases a bit, but it's still relatively good. So it's still almost below 1% only for the diffusion potential of aluminum. We also saw that the largest errors are obtained at the boundaries of the phase diagram, so where the logarithmic terms become important. Then he used these descriptions, so for the Gibbs energies and the atomic mobilities in phase field simulations. He ran 4 phase field simulations for different compositions, so 3 of them in this section, going from B2 to A2 plus B2, and then he also considered the equimolar composition, and he obtained various micrographs, which we didn't investigate further. As I said, he also developed another neural network model because the previous one I think is a very nice one, but if you do not have the coefficients, if you can only use commercial databases, then you cannot apply that one. So we also wanted to try another neural network, one that converts mole fractions to chemical potentials. He will apply it to the same system, but now he will do cooling simulation. So he starts from the B2 phase and goes into the 3-phase region. So he has to include, besides composition, also temperature, and he will also do that. And also in the phase field model, there will not only be the spinodal decomposition, but also the formation of the FCC. And these cooling simulations, they were especially interesting for access because they were trying to produce these microstructures using arc melting. So as input layers, he takes now temperature and then the mole fractions of aluminium, chromium, and iron. And as output layers, he has on the one hand, the chemical potentials of the 4 elements, and on the other hand, the atomic mobilities of the 4 elements, because if we don't have the parameters, we cannot compute them ourselves. And then in the middle, again, you have a number of hidden layers and a number of nodes. Again, he tried different settings. Okay, of the network, and we'll evaluate then which works the best. Here he uses a training set of 10 to the power 6 compositions and temperatures. Also, to make the optimization easier, he will non-dimensionalize the chemical potentials, and he also removes the exponential temperature dependence from the atomic mobilities. So here by dividing it by RT, and here by taking the logarithms of that. But then these values, they are used as input and output layers. He only optimizes the network for the chemical potentials because the Gibbs energy can be computed using Gibbs to Hem relation. Here, the optimization of the neural network was more difficult. So it doesn't fit that well as the sublattice fractions. So he tried many different situations. So different number of layers, different numbers of nodes. He also tried different what we call activation functions. So standard, we use the tangent hyperbolic, but there are also other activation functions. There is also a learning rate, that's also a parameter that you can set. And for all of them, he computed the mean average error, and then he tried to find out what are the best settings for each of these quantities. And yeah, we found actually that now this tangent hyperbolic function is not a good one, but this one is better. And then depending on the property, you need 3 or 4 layers and something like 128 nodes. So it's a more complex model than we had for the sublattice fractions, also a more expensive one. And the accuracy is also less than what we obtained with the sublattice fractions. He used this description to perform the cooling simulations. So he had a certain initial composition that corresponds to that particular point. And he initializes the microstructure using one FCC spherical precipitate at the corner, and then the remainder is PCCP2. The start temperature is 1400 Kelvin, and then he tried different cooling rates to compare the microstructure. And we use a system of 0.5 micrometers in the square. So for example, then for a cooling rate of 100 Kelvin per minute, these are the microstructures that you get. So the composition variables here, the mole fractions here are plotted using color. And then we see in the corner, we have the FCC phase, which grows in time, and the BCC phase decomposes, and it also worsens in time. If we look at the effect of the cooling rate, then if we look at an early stage, there is almost no effect of the cooling rate. So here we have 100, 400, 600, and 1000, almost no effect in the microstructure. That's probably also because spinal decomposition goes very fast. But if we wait for a longer time, then of course we see much more effect of the cooling rate. So you see with fast cooling, we have a finer microstructure than with a slow cooling. And so this is what he had to study for the comparison with the experiments. But if we look very carefully to these microstructures, then at first you would say, well, we have a nice correspondence with the experiments, but if you look very good, then you see that there is an essential difference. So if we look in the simulations, then we see that the disordered BCC phase, that the FCC phase is surrounded by the disordered BCC phase. Whereas if you look in the experiments, then the FCC phase is surrounded by the ordered B2 phase. And actually, we still don't know why this is. So I think we have to incorporate more in our model and probably also make everything composition dependent. So yeah, we think it can be interface energy. Interface energy is composition dependent. It can also be due to the way that we nucleated the FCC phase. The FCC phase was already there in the beginning of the simulations. Maybe if it's really concurrent, it will be different, but we don't know. It can be a transient effect. It can be elastic effects. Actually, these are all things that we should include into the model to understand why we see this difference. Okay, so I think it's time now, so I will go to the conclusions. Yeah, I would say that there is a bright future for multi-component phase field models. Now that we have developed these quaternary models and run some simulations, we see more and more very interesting effects that are there due to interactions between different elements. But the difficulty and the challenge, of course, is that the more elements are involved, the more data you need. Everything is composition dependent. And if you really want to look, for example, at these high entropy alloys, the composition dependence plays a role and each element is important. And so in this presentation, I have shown a number of coupling schemes that we have developed during the last years. I would say the polynomial fitting is very simple. It's also very accurate, but can only be applied to phases that behave easy. The tensor completion technique is a very theoretical technique. I think it has a lot of possibilities. It should be worked out, but yeah, because it's based on algebra and tensor calculations, it's probably not so easy to use. And then we have also applied a neural network training. Training for sublattice fractions was very easy and also was very accurate. And I think it's also a nice idea because it's just the computations that you put in the network while you keep all the physics of the Calphad model. And then we also applied the neural network training to the real thermodynamic quantities. And the question then, of course, is how to include composition dependence of eigenstrains, interface energy, stiffness, and so on. So finally, I would like to acknowledge the European Research Council because they financed all this research and also the Flemish Supercomputer Center. And thank you for listening to my presentation. And if you have questions or remarks, I will be very happy to answer them.